Weathering, mass wasting, and erosion. The rock masses which compose the Earth's land surface undergo constant change. Even as mountain building forces uplift the land, gradational processes wear down high places and fill in low areas with fragmented rock materials. Three basic processes are involved in this disintegration, wearing away, and movement of rock materials to lower areas. These are weathering, mass wasting, and erosion. Weathering processes break rock into increasingly smaller fragments. Mass wasting describes the downslope movement of broken rock. Erosion occurs as rock materials are picked up, moved, and redeposited by such erosion agents as running water, wind, or the moving ice of glaciers. Gradation, sometimes referred to as denudation, begins with weathering. Only after large rock masses are fragmented into smaller pieces can mass wasting and erosion remove and relocate the rock materials. Various kinds of rock-forming minerals fragment in different ways. But nearly all rock masses have deep, penetrating cracks called joints. Sometimes these joints are created as rocks are subjected to slow twisting and stretching movements within the Earth's crust. Columnar jointing occurs when molten basaltic lava cools and solidifies. Fault lines are places where the rocks have actually been broken and moved relative to each other. Weathering occurs more rapidly along joints and faults than on unbroken surfaces. Exfoliation takes place when granite rocks formed deep within the Earth's crust are exposed on the surface by uplifting and erosion, as in the high country of Yosemite National Park. When the overburden of other rocks is removed, granites tend to expand and peel away in thin parallel sheets. The forms which result from this unloading process sometimes appear as remarkably round granite boulders. Most weathering occurs at the Earth's surface, but it also takes place underground along joints and faults. These boulders in a California road cut were formed by underground weathering of highly jointed rock. Although geologists make a distinction between mechanical and chemical weathering processes, most landscapes are shaped by both types of weathering occurring simultaneously on the same rock surfaces. Mechanical weathering involves the breaking apart of rock materials in ways that do not change the rock's chemical composition. This physical disintegration of rock usually occurs at or very near the surface. The angular landscapes of cold regions, including high mountains, partly result from the freezing and thawing of water in rock joints. When temperatures drop below freezing, ice veins develop in joints and ice crystals grow in rock pores. Because ice increases to nearly 10% more volume than an equal amount of water, it exerts a strong force for widening spaces in the rock mass. Frost weathering is also called frost wedging. Block fields, found above the timberline in mountainous regions, result almost entirely from frost wedging. Salt wedging, which is the expansion and contraction of salts crystallized from evaporating water, plays an important role in the development of desert landscapes. This form of weathering tends to produce pitted surfaces. In many dry regions, the ground is covered with the salt-wedged debris of stony desert pavement. Mechanical weathering resulting from expanding and contracting salt crystals also occurs in coastal areas where rocks are exposed to salt spray from pounding waves. In addition, the battering action of waves splits rocks apart along weaker joints, leading to very rapid landscape changes along coastlines. Plants and animals also contribute to mechanical weathering. Plant roots penetrate joints, prying them apart. The activities of burrowing animals also widen joints in rocks. Mechanical weathering is the dominant weathering process in regions that are very cold or dry, such as high mountaintops, Arctic regions, and deserts. Chemical weathering, which causes rock to decompose as its mineral composition is altered, is most pronounced under conditions of ample moisture and high temperature. Moisture is required by nearly all chemical reactions. The positively charged hydrogen ions in water react with the chemical compounds of the rock minerals, thus causing the rock to decay. Chemical weathering takes place most rapidly under conditions of year-round heat and humidity. Weathering proceeds so rapidly in the rainy tropics that most bedrock is covered with a deep, weathered mantle made of fine, chemically altered particles. Lichens are important agents of chemical weathering, even under cold or dry conditions. These plants are composed of algae, which can produce energy through photosynthesis, and fungi, which produce acids that help break down the rock to provide nutrients. In humid regions, decomposing litter on the ground and secretions from plant roots increase the acid content of water percolating downward through the soil. Acidic moisture decomposes rock materials more effectively than pure rainwater. Accelerated weathering by acid rain illustrates this effect on Europe's ancient stone monuments. Weathering involves many chemical processes, including oxidation, carbonation, hydration, and solution. The orange-toned rust which forms on objects containing iron is an example of the chemical reaction known as oxidation. The red and brown shades of many decayed rocks and soils result from oxidation of their iron-bearing materials. The combined processes of carbonation and hydration help convert feldspars, which are common in many rocks, into soils that are rich in clays and silicas. Limestone is changed by carbonic acid into a highly soluble form that is easily dissolved in solution and washed away, thus forming a landscape marked by sinkholes and caverns, as seen at Montezuma Well, Arizona. The famous cenotes of Mexico's Yucatan Peninsula are also examples of limestone sinkholes. These cenotes have long attracted human settlement because little surface water is available in the Yucatan. Weathering processes, both mechanical and chemical, vary with temperature and the amount of moisture available. The processes also operate differently on different types of rocks, even under the same conditions. Limestone, for example, weathers fairly rapidly under humid conditions. Carvings on this Mayan stele can barely be discerned after about 1,500 years exposure in the damp environment of the Yucatan. In contrast, these Egyptian engravings are thousands of years old, indicating the resistance of limestone to weathering under desert conditions. Differential weathering of various types of rock, each with its own physical and chemical characteristics, results in dramatic landscapes, such as the step-like formations of Arizona's Grand Canyon. The downslope movement of weathered rock materials due to the pull of gravity is called mass wasting. Mass wasting is affected by the amount of water in the earth material and may take place slowly or rapidly. Loose material on a slope has a maximum angle that can be maintained. At the angle of repose, gravitational pull is balanced by the cohesion of the material on the slope. When loose materials on a slope are at the angle of repose, the addition of new material or a major increase in the material's water content results in downslope movement. Creep is a very slow form of mass wasting. Generally, the whole slope is involved, and the process is so gradual that there is little direct evidence that it is occurring. On steep, heavily grazed slopes, creep can create a series of terracets, like these above a rancher's dwelling in Costa Rica. Solifluction is a slow downslope movement of loose material most commonly found at high elevations or high latitudes, where meltwater from winter snows remains trapped in the upper layer of soil. Rapid mass movements typically leave visual scars upslope where material has been removed. Deposits of debris are found at the base of the slope. Slumping and earth flows are forms of slope collapse in which masses of soil slip downward. These movements frequently occur after earth materials become saturated with water. Mudflows are rapid movements of moisture-saturated soil. The mudflow or lahar that created this jumbled landscape near Washington's Mount St. Helens resulted from volcanic eruptions that melted snows and glacial ice on the mountain slope. Large mudflows may also be called debris flows. Great rivers of mud can do tremendous damage, moving huge trees and boulders in their paths. Rock falls occur when fragments loosened by weathering fall from very steep slopes, coming to rest at the base of the cliff. These fragments, called talus, collect as a talus slope. When large blocks of rock fall, they often roll downslope for considerable distances before coming to rest. Most landslides occur in steep, mountainous regions. They move down steep slopes at great speed and typically leave a deep scar on the hillside where the slide originated. This scar was left by the famous Madison River Canyon landslide that was triggered by a major earthquake in Montana in 1959. Earthquake Lake was formed upstream when the landslide dammed the Madison River. The Gros Ventre, Wyoming landslide of 1925 was caused when a mountain slope became oversaturated with water after days of rain. A lake also formed upstream from this slide, which dumped more than 40 cubic tons of rock into the Gros Ventre River Valley. Downslope movements of snow, rock, and glacial ice are called avalanches. In regions with substantial snowfall, avalanche tracks scar the slopes of steep mountains. Weathered materials are picked up and transported to new locations via erosion processes. The principal agents of erosion are water, wind, and the moving ice of glaciers. Water is by far the most important erosion agent. Water from rain and melting snows probably removes 50 to 100 times more material from slopes than do mass wasting processes. The effects of erosion by water are especially noticeable on barren slopes composed of poorly consolidated materials. Streams and rivers carry earth materials great distances and redeposit them far from their sources of origin. Wind is particularly important as an erosion agent in arid and semi-arid regions where there is little vegetation cover. Glaciers are extremely powerful erosion agents. Many landscapes reflect the action of former glaciers during periods when they covered a greater part of the Earth's land surface than they do now. Sharp peaks, called horns, U-shaped valleys, and glacially transported debris mounds called moraines characterize mountain regions that have been heavily eroded by alpine glaciers. Over long periods of time, the processes of weathering, mass wasting, and erosion can wear even the highest mountains down to a nearly level plain. Yet, even as gradational processes wear away at the land, other forces operate to raise new mountains.